Okay, continuing with notes from section 9.1 on sequences. Just to recap for a little bit, convergent sequence is simply a list of ordered values or a list of ordered numbers that have a limit or that has a limit and that approaches a real number. Divergent sequence, a list of ordered numbers that does not have a limit. So one that either goes to infinity or to negative infinity, and those we consider divergent sequence, or also ones that oscillate between two values without settling down on a given value or approaching a specific one value. All right, a couple of examples here. Let's look at the first one here. Determine whether the following sequence converge or diverge. So we can simply find the limit as n approaches infinity for many of these and apply rules that we've learned from before with limit approaching infinity. So in this case, n over n plus 1, we see that we have the degrees that are the same. We can take the ratio of the leading coefficients, and this gives us 1. So we see that the sequence converges to 1 because the limit is equal to 1. For b here, limit as n approaches infinity for 1 over 2 to the nth. We see that the denominator is increasing to infinity, which will cause this fraction to go to 0. And so the limit is equal to 0. Therefore, our sequence converges to 0. Here, 3 plus negative 1 to the nth. If we replace n with 1, this will make this a negative 1. So 3 minus 1 is 2. And if I plug 2 here, that will force this negative 1 to the n to be a positive 1. So 3 plus 1 is 4. And then goes back to a negative value, which is 3 minus 1, which is 2. So the sequence is just simply going to go back and forth between 2, 4, 2, 4, 2, 4. So our sequence will diverge since the limit of the sequence oscillates between 2 and 4. Okay, for D, limit as n approaches infinity for n over 1 minus 2n. We see the degrees are the same. We take the ratio of the leading coefficients, so 1 over negative 2. So our limit is simply negative 1/2, or therefore our sequence converges. For this next one here, natural log of n over n, this will converge to 0 because of what we know with comparative growth rates. We see that we have a natural log function up in the numerator. We have polynomial with degree 1 in the denominator. So we see that the n is going to grow at a faster rate than the natural log. The natural log is one of the slowest growing functions. And so therefore denominator over time will grow at a faster rate than the numerator. So that will cause this fraction to go to 0. Another way that you can do this is go through L'Hopital's rule and take the derivative of the numerator and denominator, and eventually it'll settle down to a value where we can see the limit will go to 0. So for E, our sequence will converge. All right, a next one here, n factorial over n plus 2 factorial. If we try and expand this out a bit, the denominator, we can write this as n plus 2 times n plus 1 times n factorial. And once we have the n factorial, we see that we can cancel those out. And then our remaining rule of sequence is 1 over n plus 2 times n plus 1. And this is simply 1 over n squared plus 3n plus 2. And we see that will go to 0. Our sequence will converge to 0. The denominator will increase to a value where it will cause this fraction to go to 0. Next one here, we have a 2n factorial over n minus 1 factorial. We can think of this as 2n times n minus 1 factorial, and then this denominator, n minus 1 factorial, will cancel out, leaving us with just 2n. So the limit as n approaches infinity for 2n is simply infinity. Our sequence will diverge to positive infinity. Okay. N plus negative 1 to the nth power over n. We can take the limit of our rule of sequence, and the 1 will stay, but the second will go to 0. Basically, the numerator will oscillate back and forth between -1 and 1, but the denominator will keep increasing to infinity, which will cause this fraction to go to 0, and so leaving us with just that 1. So our sequence will just simply converge to 1. Okay, next one here. We can plug in some values here to see what happens with this sequence. And if we plug in 1, we get 0. If I plug in 2, we get positive 1/2, then negative 2/3, then 3/4, then negative 4/5. So we see that the positive values are approaching 1, but the negative values are approaching -1. So this will diverge by oscillation. We have one portion of the sequence that's approaching 1, another one that's approaching -1. So the sequence will not settle on a value, so the limit will not exist. Will diverge due to oscillation. 2 to the n over n plus 1 factorial. Here, this may not be very apparent, but one way you can do this is we can look at comparative growth rates, and we know that these are both increasing at a very fast rate. But factorials are going to increase at a faster rate than these exponential functions. So this will go to 0, so therefore our sequence will converge. Another way that we can do this is we can plug this in the calculator. And if we go to our calculator and do list operation sequence, and if we plug in sequence of 2 to the x over x plus 1 factorial of x from 1 to 99, we see that this value, this sequence, will get closer and closer to 0 because this denominator is increasing at a faster rate. So our sequence will simply converge to 0. Here, 1 plus 1 over n to the nth power. Again, we can use knowledge that this is the definition for e. So as n approaches infinity, this will go to e. We can also use our calculator with our sequence method to help us determine that this sequence will approach closer and closer to e. Or we can set this as the y as a function for y. Take the natural log of both sides, go through implicit differentiation, and be able to see that our value will go to e. Right, next one here, 2n factorial over n to the nth factorial. N to the nth power. And n to the nth power is the function that will grow at the fastest rate. So that's faster than the factorial is the fastest rate. And then the next is x to the x, or n to the nth power. So therefore, the numerator is growing at a faster rate than the denominator, and so the limit will go to infinity. Our sequence will diverge. Again, we can use our calculator and type in, have the calculator determine the sequence value, and we can determine that this rule of sequence will not converge, but rather will continue to increase to positive infinity. All right, finding the nth term of a sequence. What we can do here is we can look at these values and try and determine what type of a pattern that this is following, and also determine what type of sequence this may be. We see here 3, 8, 13, 18. These values are increasing by a constant of 5, so we can think of that as an arithmetic sequence, and the 5 being the common difference. So if we plug into our arithmetic sequence formula here, a sub 1 being 3 and d being our common difference, and if we solve for a sub n and clean this up on the right side, we get 5n minus 2. And we see that this sequence will just continue to increase to infinity, so therefore our sequence will diverge. Okay, for part B, we see that this sequence is following a pattern of a ratio of 3. So this value keeps increasing by a product of 3, by a factor of 3. And this is simply a geometric sequence where each value is increasing by a product of a constant. And our formula for geometric sequence is a sub 1 times r to the n minus 1. So we simply plug into our formula 5 times negative 3 to the n minus 1. And we can simply see that this will just keep going to positive and negative infinity. So this sequence will converge. Sorry, will diverge. Next here, 1, 4, 9, 16, 25. These are all perfect squares. So a sub n is equal to n squared, and n squared will simply diverge. 4, 10, 28, 82. If you look at this pattern here, this is similar to 3 squared, 3 to the nth power plus 1. So this is 3 squared plus 1, 3 cubed plus 1, 3 to the 4th, which is 81 plus 1, which gives us 82. And so 3 to the n plus 1 will simply diverge. Next one here, 2, 3, 4, 5, 6 flip in the numerator. Denominator is 1, 3, 5, 7, 9. We can set up a rule with the numerator being n plus 1, the denominator being 2n minus 1. And if we find the limit as n approaches infinity of our rule of sequence, the degrees are the same. We look at the ratio of the leading coefficients, we get 1/2. So limit is equal to 1/2, so our sequence simply converges to 1/2. Natural log of 1, natural log of 2, natural log of 4, natural log of 8. This is all increasing by a factor of 2, so 2 to the n minus 1. And we see that this will just keep increasing to infinity, albeit at a very slow rate. But the sequence will still diverge to positive infinity. Okay. Find a sequence whose first 5 terms are given here. Then determine if the sequence converges. And this is similar to what we see here with D, with a base of 3, with a base of 3, and we're simply, instead of adding 1, we're subtracting 1. And then the denominator, 1, 2, 6, 24, these are all factorials of n. With negative 1 to the nth here, showing that there is a change in signs, alternating signs for each term. And if we take the limit as n approaches infinity, we see that the n factorial is going to grow at a faster rate than the exponential function. So therefore, the limit is equal to 0. So our series will converge to 0.